大家好，我是王不老说半岛。Hi, folks. Today I'm going to continue my topic about the reliability, and I would like to compare CMOS reliability versus packaging. Let's see how two can compare with each other. Eventually, packaging is going to the back end of line process already, so they are eventually going to match the CMOS reliability in the future. Let me first by giving you a highlight of the CMOS reliability. Basically, reliability is trending down. All right. You can look at the graph below, and the mean service lifetime is getting lower and lower. All right. It seems to be flattening out, but the recent data is still decreasing. It's not getting better. All right. That's current trend. And what about packaging reliability? I could only say it's a TBD, right? It's still evolving, and many new technology being introduced, many new type of packaging being introduced, many new material being introduced, and we give it a very harsh example, a 3D stack, a CPI, a chip packaging interaction nightmare by looking at the HBM on top of logic die, and this baby is heating up like crazy, and this is a DRAM that cannot tolerate high temperature. Uh, it starts to forget stuff at 85 and it's fully absent-minded at 125 degrees Celsius. All right. So that's pretty much the key message I'd like to convey to you from this talk. But we still need to go into the details, right? To start with an easy icebreaker. The statistics. We're talking about reliability. We have to talk about reliability statistics and statistics. That's the origin of everything we study, right? We need a tool to study reliability, and we have to use statistics. But what about statistics? Some people argue that it's not actual science. Right? It's not like the Newton law that you push something and the force come back in opposite direction. The top three law, the quantum mechanics, everything seemed to have a reason for those very solid science, but not so in statistics. We're talking about probability. Nothing is 100% accurate, right? And at the end of the day, statistics only make sense when you have good data, right? Otherwise, you could fall into the garbage in, garbage out traps. All these guys, when they have the distribution, and they always argue you need to have a certain amount of data. The more the data, the merrier. So as your statistics distribution will be narrow, right? That's the central limit theory, right? But let's look at that from a reliability perspective. We introduced the Note 7 reliability last time, okay? And we introduced the desktop and said that the Note 7 and iPhone, they have these early failures. And reliability has three modes: the early failure, the random failure, and then the wear out failures. And these three lines, the composition of three lines form this bell-shaped curve, okay? And we try that how do you describe mathematically in the language of statistics for this best up curve? It turns out Weibull, Walodi Weibull, how developed this. He proposed a special Weibull, the probability density function. This is not the PDF file we're talking about, right? It's a shorthand for probability density function. He gave a very beautiful presentation of his formula, right? This is the formula he used. And has a power law and exponential term. And later he reviewed that this is a failure rate, the first portion. And the second portion is your reliability functions. This reliability function is a mathematical form to show reliability in a certain conditions. So it's not reliability itself. All right. Reliability we meant is like a general term, and reliability function is a specific mathematical representation of a specific reliability conditions. And you can use Perplexity AI to describe to you and what happens, what's the difference. You type this prompt, and you will give you um, very clean explanation, better than what I can give you. All right. The let's look at the form, what this parameter, this beta, eta, let's ignore this for now. This is a schema for now. This is time variable, all right? Everything is time variable here with two very famous parameter is beta and eta. Okay, let's look at this cartoon and see what they means.
Named after Swedish mathematician Velotti Weibull, the Weibull distribution is heavily used in reliability engineering due to its versatility. The three-parameter form looks like this, where the left part of the formula describes the hazard rate or instantaneous failure rate, and the right part of the formula is the same as the reliability function. Eta is the scale parameter of characteristic life and changes the values that the distribution falls around. Beta is the shape parameter and changes the shape or spread. And gamma is the location parameter and shifts or offsets the distribution. Using these three parameters, the Weibull function can fit infant mortality or early life failures, failures that occur randomly, and also those for wear out or end of life.
Yeah, this beta value, the shape factor, is one of the key parameters that were of interest here. The shape parameter beta, when you're less than 1, is like a drop like a rock. It's an exponential. It's not exponential term, but it's drop like a rock. And the beta equal 1, that means the failure rate will reach a constant. And then the beta greater than 1, meaning that you're in wear out. And so using beta only, by keeping a scale parameter the same, you could see that beta is adequate to describe the falling from the early life, is beta 0.1 here, all right? And then this beta equal to 1, which is your useful lifetime, and the wear out, that's gradually decreasing the things, everything going to the end, everything must die eventually. So that was the kind of intrinsic failure of the device, of the package, right? So Weibull distribution used the shape factor to represent the shape. I see here, this is falling shape, and then this is a flat one going to here, a beta equal to 1, and this is the wear out, right? So easily, he using one formula just by changing the shape parameter, and he could get very clean reliability best shape, all in one form. And this is called a PDF, probability density functions. And in statistics, once you get this right, everything will naturally follow through, all right? I give you an example. In Weibull, mean time between failure, this eta, if beta is equal to 1. So this means the expected, which means just expected value. We just integrate this against the variables, get your expected value. Then you got this immediately. So all these, the eta that you obtained, okay, is the characteristic lifetime of your package. And so this is very well known. So that's the beauty of the Weibull. The Weibull parameters, it could give you the 3 modes of interest and the lifetime of the product. Beautiful, right? That's so beautiful. And now what tool you can use to calculate? Well, the Weibull, you Excel Weibull distribution to get the value, whatever you want. Let's do an example. Weibull, Excel Weibull functions, Weibull distribution. For example, here, a component with a shape parameter 1.5 and a scale parameter of 100, all right? you could calculate the probability that a component will fail within 80 hours. Right? The scale parameter 100 means that mean time between failure is, the value close to that. And then you have alpha is, your beta, your shape parameter is 1.5. And then you're looking at the 80 hours of the component. What is the probability that the component will survive? So the Weibull.dist distribution give you the area here. This is your probability density functions. The integration of your probability density function is the probability. Please make this, I hope I can make this clear to you. This probability density function is not probability. It is the area under the PDF is the probability. Okay, so just be careful. Okay, and don't get yourself confused. Okay, this is not probability. It's called probability density function, but it's not probability itself. The probability comes from the integration of these the formulations. Okay, so this example tells us that if you find out your Weibull, this is how you find out your Weibull. By when you have a product ready, you know your Weibull distribution, right? You know your scale parameter, and you know your shape parameter. This is called two parameter Weibull. You know that, the rest is history. And then you're asking yourself here, what's the probability it will survive, right? It will fail, right? Here is the component will fail within 8 hours is 51%. And the other way is the probability that it will not fail, right? That's 0.49. Very obvious. Okay. Now to understand this parameter better, let's use I would call a dimensionless form by rearranging the formula here, the fail rate. Okay. What we did is that we take the failure rate, all right, and rearranging it in a way so that, and then against the time variable against the time versus tau, then everything become one graph, and then you could compare with different beta, right? And you could, by looking at this, the beta, the red line is 0.1, 0.2 is a blue, 0.5 is a green. I ask you a question. Who has a smaller beta, Note 7 or iPhone 15? Okay. And here it looks to me that the fail Note 7 seems to be a little bit worse than the iPhone 15 Pro. And from that perspective, meaning that the Note 7 beta will be larger than that of iPhone 15 Pro, even though both are less than 1. Okay, they are all falling into this early infant mortality failure mode, and however, the Note 7 seems to do a lot worse, a lot quicker, and so that means to me the beta is a little bit larger. This you could usually look at, but on this graph you can clearly see that. Then what about beta? Okay, which one is better? 2, 3, 4. Which one is worse? That's an interesting question. Let's hold that question. Let's hold that thought for a while. Okay. Beta equal to 1. Greater than 1. It means that the rate of failure is increasing over time. That is bad. This could mean that the device is not well maintained or is subject to extreme conditions and is increased the likelihood of failure. Some people argue that this intrinsically something bad happened to the parts or to the package. That's what it's trying to say here. The rate of failure is increasing over time. This intrinsically bad, get worse condition is triggered by the external extreme conditions, or it's not maintained properly, something bad happened to the device. It lost the strength to withstand. Okay, and then let's look at GE's guideline here. The beta greater than 4, poor machine design. It means it's weak, right? Poor material selections. Okay, all these are telling me that it's not strong. The stuff is not strong. Okay, it rapidly wear out. So beta much bigger than 1 is worse than beta. It's close to 1, maybe 2, 3, right? 4 is definitely worse than the 2 or 3. So this gives you a hint. If you look at the whiteboard, once you get the whiteboard done, right? Once you get the whiteboard done, what I mean is that you have found your data, you collect your reliability data, and you plot your whiteboard distribution functions using your data to get the beta value and eta value. Then you could use that value to determine the quality of your package. Beta equal to 4, meaning that quality is bad compared with the smaller beta, right? So that's what these parameters is trying to tell you. And eta, mean time between failure, as we mentioned here, is when the eta, when the beta equal to 1, the eta, the time variable you obtain here, is the mean time between your failures. Okay, this is very interesting too. This is where your warranty comes in, right? Your warranty has to be smaller than this, or your mean time between failure has to be greater than your warranty. So current design, hopefully 2-3 years minimum, right? And ideally, you want 10 years. In old days, actually, CMOS or microprocessor can really last 10 years. But nowadays, you know how it goes. And on the poor part everywhere. So mean time between failure is like a couple years only. Okay. So these values are very important. But to get that value, sometimes confusing, can be misleading. And let me give you an example. If a population of 500,000 and 1,000 people die of random cause at 10 years, then you use the mean time between failure, it would be, putting the formula into it, you got 500 years old. This obviously does not make sense. People cannot live 500 years old, right? So what does it mean? It means that mean time between failure, it provides some information about reliability, but maybe inadequate to fully understand the overall reliability. Okay? Or the mean time between failure is meaningless if there are multiple failure modes. Here you assume a random cause, but the data may be not random. Maybe this guy has something else going on, right? So all that we have to be very careful. So what I'm trying to say is that you can get your data and then fit it to a distribution. Many software can do that and get your whiteboard parameter shape and scale done, but you need to be very careful in handling those data. Okay, don't be go blind. You need to go to it and say, "Oh, this is what it means. This is what it means." You need to have a physical sense in your head to have high confidence in the beta and eta parameter you obtained. Okay. Now, what are tools available for you then? Well, this is a Webstar tool. This is a Minitab, NRST. Let me show you these tools a bit. Okay. It's a very interesting tool for you to have, right? If you look at the website for the WhatsApp, the website give you a free statistic and forecasting software. You could run this program, okay? You could run this program easily, and then so minimum value shape parameter 1, maximum A, okay, width is okay. It is compute. See that? All right. This gentleman used R program R to write this for you, so you could get your shape scale very easily, right? By inputting this is the data he inputted. You could change this value, and then you could get your result. This is a Q plot and whiteboard distribution. Later we'll just describe what it's about. Okay, this free software lets you play. So when you have data, you play with it. And then the Minitab. Minitab is what I've been using all the time because it's really powerful, right? And for example, you could use to analyze a very complex whiteboard failure mode, like multiple failure mode. If you follow uh, this sequence in the software, you can easily get your results uh, very easily. And this software is now mostly free to many universities. Or you could download a software and play with it for 1 month free of charge, or download some old version completely free. Okay, but the old version is good enough. They don't change much. Okay, so all these help you to analyze. And big company, uh, sometimes you jump, sometimes use other software. They all adequate. It just depends on user friendliness. I like this because, well, I use it a lot. That's the reason. Okay. If you use Jump, you get the same results. The I try to convey is that tools are everywhere. Free online tools are everywhere. So just spend time and play with it. You gain a good hand of it, right? And then the NIST. Uh, NIST is also a very good website that helps you to study the whiteboard plot. Okay, so this is NSD has Engineering Statistics Handbook, and you could go over this, everything put inside, even include the data set, how they plot this one. It's very nice. NIC did a very good job in teaching people how to use it. Because they include the data they use, and then they include the results, and then you could use the software here to get the result you want. So that's the beauty of this website or other free website. This is one I find out, and then it's very convenient. And then we have discussed to some extent last time about this board level reliability for the embedded processors. This is a TI report, okay, from the Texas Instrument report. They show that the board they have with the package, which standard package, they use the typical whiteboard 2 parameter plot. This is one they obtained from, right? And this is the red line is a confidence line. It seems they are fitting reasonably within this confidence 95, could be 95% or 90% confidence intervals. So this is reasonably good data. Then my question for you that um, how can we tell if these data obtained are good? First of all, to to do your reliability analysis, you need to find out are they good enough, all right? And this plot visually probably okay. And these 2 parameter variables sees the weakest link in the system. If something else go over, then you know it's bad, and you need to find out what went wrong, right? And then Nielsen 2 parameter variable can really help you, or at least from the NIST. Now, if you plot your plot in the Nielsen manner, which log scale in this direction and the whiteboard probability on the y directions, and then according to your rule, and then you could add the 62%, 63.2%, you got your beta. All right, at that point, intercept will give your eta. So from this plot, from the Nielsen plot, you could easily get beta and eta immediately and clean it. And on top of that, the least square fit here, if every point is close to that, you know the data is good. If you see something wacky, right? If you see something wacky, then they're no good and no good. All right. If you see a data here, or weird, then you know this fitting is not comprehending all the data, and something else is wrong. So this plot give you a good tool to get your beta and eta. So pretty much, so once you plot this 2p whiteboard, Nielsen 2p whiteboard, the data answer these questions. Do the data follow a 2p, right? And what is the best estimate of shape parameter? Because if your data is scattered everywhere, then using this method, 6.2 point, then you can get your beta and eta quite reasonably well. And this is, he proved it, he has proven it statistically. This is best estimate. So it gives you the best estimate for the scale and for the shape parameters. Well, then people might ask, well, is whiteboard only one I could have? Whenever I see a probability problem, do I always use do I have to always use whiteboard analysis? Well, the answer is not really, because some conditions you could benefit by using log normal or not normal. The log normal is better to assess the fatigue stress on mechanical system. This is very famous. And then it has a skew distribution. Okay, it has a lower value means a lower mean value. And lower value means, and your data is kind of have a large variation, a large standard variation, and all positive values. So your distribution like this, right, is here, is skewed. Skewed means that it's not like this normal. It's skewed, meaning it's heavy on one tail, and then the low value here, and then the sigma is large. And you would take a natural log of each random variable, and it becomes normal. You take a log of the data you have, and it become very normal. Then the log normal is the best, right? And its formulation is very close to the normal, except you have more variable. You have a variable in the denominator, and log here. Your variable is log x. Everything in the same form. All right, but you have these two distinct difference. Log normal is very famous, also say in stocks, in the stock forecasting model that predicting the value of stocks. Right, so people using that, and here's a fatigue stress that the mechanical engineer use a lot. That could be also benefiting the package reliability. Your package is fatigue stress related, right? That could be a useful tool. So just FYI for this one. So is packaging reliability statistics reliable? I would like to ask the question for you. Yeah, if you know what you're doing, of course. Things happen for a physical reason. This I would like to stress, right? If you've seen some anomaly, you need to find out what's physically why it went wrong. And then please do the due diligence by removing the early failure mode out of the way. So when you're performing all these analysis, if you see outlier, all right, mostly they're early failures. You need to really, really figure out what went wrong. Suppose you have this cycle, right? You have some data here, some data here. You need to remove it, otherwise you change the distribution greatly. And this early failure here, meaning there's something, just maybe it's just stupid error, some stupid errors, okay? And somebody forgot to close the door, or they forgot to put a pin, something stupid. It's not the reason you want to study. All these studies is trying to actually study the wear out aspect. That's what we are trying to do. Now, at the end of the day, this is what we're trying to do. We want to understand the wear out better, so as when we design something, our useful life can be extended, right? And we want to remove this from the get-go. So this one, we need to take care of it, right? Or later by our burn-in, or do a good design by reducing this to negligible level. And the purpose of reliability study is to extend the line. as far as I can see. All right. In order to extend it, you need to know the wear out failures. And that's what we're trying to do here. And in order to study the wear outs, you to get this curve like this, these are all sort of trying to do the wear out, right? All the flat part. And then the outlier here, you really need to remove them by knowing what went wrong. Okay. And so end of the day, the packaging reliability, is it good? Is it reliable or not? Depends your personal interpretations. But your homework is to get the early failure out of the way. And if you need to watch out for the multiple failure modes. This is probably the hard one. The multiple failure modes, your data is very scattered. All right, you have many parts, right? Right. Some have the logic die part, DRAM part. If you can identify their failure could be because different reasons. For example, HBM, as we explained earlier, this HBM failed because temperature. Okay, right? When you go above 85, it went nuts. So this is a temperature effect. And then the failure of the logic die will be different, something else, right? Maybe your gate oxide depth too thin or something like that, right? It's different from the HBM. Okay, that is what I meant by multiple failure mode. And for the multiple failure mode, you need to use more advanced software. Minitab will take care of that, right? Using parametric distribution analysis, and then you could analyze multiple failure mode rather easily, right? We're not going into that detail. Just tell you what the purpose of this presentation is tell you what's the resource available for you to moving forward, and what kind of mindset you should have in dealing with reliability statistics, especially relevant to the packaging. Okay. So with that, let's move on to let's review CMOS reliability because that's what we learned tremendously from. Everything we learned there can be ported to the great extent to the packaging reliability because packaging reliability eventually going move into as the back end of the CMOS. Okay. So the question for you is that are they more reliable at scaling? Well, the answer is no, right? They are actually not. Overall, as I mentioned earlier, that the CMOS reliability goes down as the years go on. The mean service cycle, usually, very old days, very robust. It could run like 100 years, but now it's like, well, way below 10 years, a couple years now. It's common. You look at your own cell phone, you look at your own laptop, how long it will last. If it lasts 3 years, you're pretty happy already, right? If it lasts, 5 years, you're really surprised. If it went by 1 year, you will be unhappy and try to get a warranty through Costco, right? And why is this happening? Okay, this is because the CMOS beta, the shape parameter trend, go down. Right? Thinner oxides, area scaling, all right, getting smaller and smaller, chip gets smaller and smaller. And this means that the failure rate increases and viable beta decreases. So this famous paper show you that when the oxide get thinner, your slope get smaller, right? The thinner oxide decrease slope beta, and this is your CDF, the cumulative distribution functions. That's the probability. This is the probability of failures. And you can see clearly that the CMOS beta trend doesn't look good because we are moving into that directions. Our oxide thinner and thinner. So this is old data, but the high K oxide right now is like 2 to 3 nanometer. So getting thinner and thinner. I'm talking about the physical thickness, not EOT. Okay. And something even worse happens. It turns out that the beta trend getting worse from both sides. which means the beta approach unity. All right, from both sides, from the way out drive, from the way out intrinsic one here, and then the input motility on the left-hand side, and the wear out intrinsic on the right-hand side. This is really bad. Let's look at. I mentioned, many times that the purpose of reliability is to push this open, make this top wide, make this best top wider and wider, so you could comfortably sitting in. You're taking a bath in the bathtub. The wider the bathtub, the better. But in reality, it's not. It's getting this. The earlier area and then the way off area come together. All right. They have this beta approach unity. Okay. They approach this unity from the both sides. The input modality it's getting close to 1, and we're out. In 1990 is beta equals 3, and then 2010 is 1.2, right? It changes from 3 to 1.8 to 1.2. It is bad. It is really bad. Okay. So why is CMOS reliability getting worse? It's because we always try to rush the market. Look at the iPhone, Samsung phone, Pixel. They come up with new product every year these days, right? So they are rushing to the market with more advanced process technology, and they meaning that the foundry had less time to optimize the process, and it's difficult to test. There's a lower testability because the process steps are increasing too fast. For every generation, you are adding like 50 steps and 50% of metal layer. Okay, so that's currently trend being observed. And then with a weaker material, what I mean is that the thinner oxide and then metal had to be thinner, right? Everything had to be thinner because you're scaling. You force everything to be a weaker, intrinsic weaker stuff from scaling. On top of that, there's no sharing of IP. I don't want to share my IP with you. I solved my problem, so expensive process. Of course, I'm not going to share it with you with a paper or with some spec. Right? So you're not sharing. It's good for you, of course, for one foundry against the other. The TSMC will never tell Intel or Samsung what they exactly do to make the 3 nanometer work. From the business perspective, make total sense to TSMC, but from the reliability overall, the overall economic, I mean the whole environment per se, Intel still producing the chip, right? Samsung is producing, everybody producing similar chip, and then your reliability is better, but the overall population get worse. So I'm not going to share with you. So that's what I see right now, and then because the time the rush to market, the just enough mentality, meaning that, oh, I know that my warranty only 2 years. So I'm not gonna, do more work to increase my reliability to 10 years. Of course, that does not make sense either. But that mentality eventually reduced the overall the overall systems, the world, CMOS worlds, bio world, the robustness. Okay, then they reduce the margin for become a more robot. Right? The whole system is less reliable. That's why the whole world reliability in terms of CMOS is getting worse from my perspective. But does that mean that we don't understand what's going on? Well, that's not true either. CMOS reliability understanding, it has advanced into an atomic level. Okay, people now can use first principle to calculate where the defect coming from and what exactly they do, and then generate another model, and then all the way to finally go to the circuit and go to your inverter and figure out what will impact to your device. So this atomic defect-centric evolution is very clean now. Okay, there's a famous war going on between IBM and IMEC in terms of what exactly the defect mode look like. And then this picture shows you that this EP fit is a better fit with compared with DS. They are pretty good in the early one, but at the end, the tail one, EP fits better. This is what Intel did in 2014 in the IRPS. And they show that they don't know what, right? They don't know which one is good, which one is bad. But if they compare with the IMEC model, this IMEC EP model and IBM DS model, okay, this EP model is exponential, Poisson model is a defect centric, and then the EP model is a little bit different model. Or it's not log normal, something else, as in using a new distribution. And then use their data. You see, they use 92,000, sorry, there's a typo here. Intel used their own 92,000 FinFET data to find out fit that EP is a better one. This model proposed by IMEC, right, by Ben's group, my friend Ben's group, very good, the expert in reliability. Their model fits better, okay, compared with the one suggested by IBM. And then the IBM DS model, you can look at this data. This is data they fit it with a log normal and then normal. They say the reliability data, okay, all these data is not log normal or nor a normal, right? Because the tail doesn't fit, only a portion of distribution fit. So this one is, oh, no good. This is a short one, 10 second, and this is a 10,000 second slow defect, fast defect. And then they find out, oh, neither. They're not this, they're not that. And they propose a dispersive skeleton TS model. So what they did is that they changed the PDF, the probability density function, from normal along normal, which we mentioned earlier, right, to the specific dispersive scalar model, TS model. And then that's what they proposed to explain IBM data. IMEC exponential Poisson model, on the other hand, proposed differently. It says that they have the random noise, the short term, and then the long term. It's two different time scale one. The stress time is this is see the 1900 second. This is zero. Initially, you have it. You have this random noise. Carrier talking to the gate, and release it, coming back and forth, coming back and forth. And then the long term one, there's a drift, a signal drift. The drift is your reflecting in your the threshold voltage drift. You drift up, okay, at high temperature. High temperature means that you are accelerating a process to make it happen, so you can have a signal. Otherwise, you take forever to get a signal, okay. And so all these, he proposed here they propose a different mathematical form, and that makes sense. Making sense to them, and it turns out they did a much better job. Okay, once they have that, you get that done, then they use the data, they fit it with the new PDF. Okay, again PDF again, probability density function again. Here they use this form. They use this form to fit their data. To fit the data in a way, compare the DS model from IBM, and then Intel used their formulation with their data fitting and find out that EP from IMEC is a better one. Okay, so that's pretty much what it meant. And all these are trying to do to analyze, focusing on the wear out of gate oxide and interface. Pretty much that's the CMOS reliability is doing. Of course, you had the hot channel injection, and then TDDB. All these are important. All they are important, right? But if you look at the trend, this is no longer important. This is your dominant. This is dominant, but not. This is hot channel injection is no longer hot carrier injection is no longer important. The reason being this. The reason being that the VDD drive, the voltage drive, is when if you have a high voltage, it means you have a very high field. All right, high field, then the hot carrier injection is important. This is important because here the hot carrier injection is because the field here become very large. The field here attract electron here, accelerate, and then boom, it bang into the drain, and then create a lot of bad electrons on holes, and come in and hurts your gate oxide because your gate oxide is biased. So going here and hurt it. See here, it hurts the gate oxide. It deteriorates the device. So it's a field-dependent mechanism. So when the voltage is decreasing now, for the right now we are at 0.7. So our voltage right now, VDD is 0.7 volts or lower. So HCI is no longer very important. Okay. The current CMOS reliability is mostly about VT shift, right? The VT shift is not that important in the packaging, but it's super important for the logic chip. The reason is this. This is when you design time zero, okay? And then if it operates for a couple of years, it's dripped. It drips up or broadened, but overall it dripped up. It dripped up to more than 50 volts. If this is 50, then you are in trouble. Call me out loud. The reason is that the VT range of CMOS is very small, only say 100 millivolt per VT. And that's the range you could work on. If you are, say, 2050, then it's half of it. Then the device will be doomed. Okay. But this is not a battery explosion type issue, right? This is not a No 7 issue. So let's be careful. Okay. So this is packaging related issues. It's not with the device. It is with the assembly of a defective or not well-made battery into the package, right? And overall, CMOS wear out arises from the carrier interaction with defects. This model, right, just published, clearly simulate everything you need to know about how the defects interact with each other, and then using this model to calculate. Eventually, they would go back and then feed into here. The data will feed into here, and then you will figure out device transport, and then you could go into your compact model and circuit, and then eventually your device, the actual device. So this is how good they are already. But it's still, so we know what happened. But is there anything we can do about it? Well, it still had a problem because even though you know what's going on, you could do only so much to make the device better. Because, again, as I mentioned here, you're rushing your product to market, in 1 year, generation by generation. 14, 15, everything is almost only a year also apart. It used to be 2 years or 3 years. Now it's 1 year because the company want to make money, right? They fool the customer like me to buy new iPhones and or new Pixels, and that's because it's new. Functionality wise, they improve a little bit. Okay, a lot of functionality I never use. All right, so that we've been fooled, but that's what's happening right now. The ecosystem of the CMOS world is will make the reliability not as good as before. It's getting worse. That's true. But will that happen? Okay, to the packaging reliability? It's a good question. It's still evolving. And then the problem with the packaging reliability to me is that the good and clean data are expensive to come by because every part you put it on comes with a huge cost. So this means that you are making a very expensive espresso machine and with a few parts, pretty much. Right? This espresso machine is like a couple $100 to $1,000. And every part to be perfect. If it's not good, then you're in trouble, right? So, but to make it good, you need a lot of data. That's what I said, right? Let's make statistical work. You really need to have good data. You you need to get good data, and otherwise you will fall into the garbage in, garbage out. Or just like what the Samsung or iPhone had, they could not, for some unknown reason, their beta value, they didn't figure out how to solve that because they had no time. They thought they were a problem. They solved the problem. So their test sample, obviously, population is not enough to represent the real one. So when you go into the real world, boom, the problem comes in. So all these because rush time to market is shortened, and everybody competing, 1 month ahead, 1 week ahead of you, and that create a lot of problem, as we know. And so that's the current status. Yeah, that's so. Are we more reliable now? I really don't know. CMOS is getting worse. Packaging is still evolving. That's what I can say right now. All right. Thank you very much.